I'm going to break this video into two main sections. The first part will be me explaining the purpose of each component, and the second part will be practical examples. So if you feel like you've already got a good understanding of why each component is there, feel free to skip to this time. Otherwise, feel free to keep watching. So starting off with a really simple version that you may have seen of a Class A amp. So this is a very simple version. It's just Vin feeds into the base of an NPN transistor, and on its collector there's a resistor here, and Vout is just also tied to the collector. So this is a very simple version, but in reality it's not a circuit that you would generally make just this. There are a few other components that you want to add, which I will go through now. Okay, so this is a lot more components, and it may look a lot more complicated, but I'll go through each part and explain the purpose of each component, as well as rule of thumbs you can use, and try to explain also the thought process behind those rules of thumb. Okay, so first things first, why even have a Class A amplifier? Well, most likely you have some small AC signal that you're trying to amplify, either its current or its voltage. So with that assumption, we can say that Vin looks something like this. Just some sine wave. And we also don't know that Vin, whether it's centered at ground or at some arbitrary DC voltage. So it has this AC fluctuation, but it could be fluctuating around, for example, 5 volts. So that brings us to the first important component, which is this capacitor here. So if we just did a simple circuit analysis of a voltage source and a capacitor, in practice what will happen is that this capacitor will charge up and equal whatever voltage is here, and then stop taking any current. So if we bring that over here and you ignore this AC fluctuations, the capacitor will charge up to whatever DC voltage is here. Well, it'll be the DC voltage here, which let's say it was 5 volts, minus whatever voltage is at this node here. So it may not be 5 volts, but for now let's just say this is ground and that it is 5 volts. So this capacitor will charge up to 5 volts. Again, that's not what actually happens, but for simplicity. Now what happens to the AC signal? Well, you can model a capacitor not just in the DC, but in the AC. And what a capacitor goes to is this equation here. It's impedance, which is 1 divided by 2 pi f, I think frequency, 2 pi f times c. There might be a J in there, but that's just imaginary part. So, in the AC sense, a capacitor basically just acts like a resistor. Impedance is in ohms. So, for the DC signal, it gets completely blocked, but the AC signal is allowed to pass as if it was just going through a resistor. With the capacitor part out of the way, let's move on to the next part, which is these two resistors here. So the first thing I'm going to do is actually remove them. Let's say you feed your signal directly into the BJT. Well, since we have this capacitor here, it's going to be an AC signal centered around 0, which is a problem because for a BJT, there's a minimum voltage here, which essentially acts like a diode, before the rest of the amplifier will conduct. So this is around 0.5 to 0.8, somewhere in that range. And unless you exceed that voltage, the output is not going to show anything. So you're going to be losing a good chunk of your signal. It depends, again, on what level your voltage is. But in the end, you'll lose the entire negative portion of your wave and some portion of your positive. So that is if you just directly connect it. Instead, if we put two resistors like this, that looks terrible. what we can do is artificially bias the voltage here to be at that conducting point. So if you need around 0.7 volts here to conduct, what you can do is take VCC through this voltage divider to get that. So if you need 0.7, the voltage divider equation will be we have VCC here, you want that to equal 0.7, and you're going to multiply that. If we do R1, R2, it's going to be R2 divided by R1 plus R2. So you can choose, since you know what VCC is, you can choose the values of these resistors such that it is biased for this point to be already at 0.7. And so now if you have some AC signal coming in, it's going to fluctuate, but the transistor will already be conducting, so the signal won't get lost. It'll show that small signal fluctuation. At this point, you may be asking yourself, didn't we invent this problem? If we just didn't have this capacitor here, then the bias wouldn't be an issue because we know that the input can ride some DC offset. Yes, that is technically true, but you don't know what your input voltage is going to be offset by. If you can choose to offset it by 0.7, you could maybe choose to do this, but oftentimes your signal will not be precisely at the bias point you need it to be. And there's one other point too, which is when you bias it like this, if this transistor starts conducting too much, the voltage will drop across R1 more, which will stop it from conducting extra. So it's kind of another, when you bias it like this, you have more control over how much current you're going to be putting through it. There's the issue of thermal runaway, but I may get into that in a second. Okay, so next up is going to be this section here, and I'm going to start with this resistor, also known as the emitter resistor. So its purpose is stability, primarily for the DC biasing. So you may ask, how does it do that, and why would you want that? So it employs negative feedback. So as you can visualize here, if you have current going through this transistor, it's going to go through this resistor, which means that the voltage here, VE, will increase as you have more collector current. But if VE increases, and we know that this point here, VB, is being set by a resistor divider, that means if this VE goes too high, this junction will stop conducting. In reality, it finds an analog stability point. So that's how it works. As current increases on the collector, this will find a stability point so that the IB, so that the current going through here will generate just enough collector current. You may ask, what causes these fluctuations in IC that would be a problem? Well, there's two ones I'll say. One is called thermal runaway. So as a BJT heats up, the voltage required at this junction here decreases. So if you have enough current running through this, the voltage drop here decreases, which will increase collector current. So the emitter resistor helps with that because, again, more current, it will bring back the bias point, or it will increase VE, which will balance this out. Another example would be if you have some offset or fluctuation in VCC. If you had that, then this bias point over here would be higher than it was supposed to be. But again, the emitter resistor will account for that because as the current increases, it fights back with negative feedback. Okay, so there are other parts that the emitter resistor, like there's other things it does and it's useful for, but that's the main point I want to get at, is it's a form of stability. As for this capacitor here, if you have this emitter resistor, it will decrease the current that is allowed to flow through the system. Because if you increase collector current, it would cancel out. That's why the capacitor is here, because since you're trying to pass an AC signal, you don't want to deteriorate it. You're trying to amplify it. And when you provide a capacitor here, similar to as we saw in this first capacitor, it acts as a separate path for AC signals. And if you choose the capacitor value right, this path can be very enticing. It can be very low. So you could, in theory, this capacitor is 1/10 of RE. which means that there's less negative feedback, meaning it gets amplified better. So that's kind of what that's what that capacitor is for. It's the bypass capacitor to allow your AC signal to still get amplified while still getting that DC benefit of negative feedback. Okay, and lastly, the component we saw in both examples, this is the collector resistor, RC. So RC has several roles. It is what amplifies the voltage of your AC signal. It also sets the midpoint for the DC voltage. So as you can imagine, if you're passing in a signal through here, the current here gets amplified through the transistor, meaning that the voltage at the output will be IC times RC. Well, technically it's VCC minus that, and that's what Vout is. So if you change the value of RC, you're going to change Vout. And in the AC signal, that means if you have a larger RC, you're going to get more voltage gain. I also said it was for the DC midpoint, and if you only view this in the DC sense and not AC, we can see that we probably want this point here to be around half of VCC. That way it has enough room to fluctuate equally. So then you can choose RC based on your desired IC to set this to be half of VCC. And so if you know what IC is supposed to be, you can solve this equation. Okay, so now that I've gone over the purpose of each component, I'm going to go over some practical examples so you know, okay, how do I actually choose these values, and also give you the formula so whatever the situation you're in, you can think on, okay, here's how I step by step pick the values I need. Alright, so let's do a practical circuit example. So let's say you have a microphone and you want to sample it into your computer. So we'll go ahead and set up the circuit for that. So you have some microphone we'll model as just an AC signal source. We'll run it through our amp setup. And we'll say that at the output, we'll just put an ADC or something. And we'll say that this ADC has a very, very high input impedance. Something, we'll just approximate it as infinity. So that means we're not going to have to really put any current through it, meaning we can kind of ignore it when we do our calculations. So we have this circuit, but we need to also define some form of constraint for us to make decisions. So let's say our audio signal is coming in at 4 milliamps amplitude. So that's set. Let's start with what VCC is. So you get to pick this depending on your situation. In ours, we're not really constrained, so I could pick 12 volts, but if you're working with some circuit that only has 8 volts, then that'll impact your calculations. But let's say 12 volts for now. The next thing you have to decide is what is your collector current. So in this scenario, because we're putting a very, very, I guess, light load, which would be large resistance, we don't really have to consider how current is going to flow into it. So that means IC is somewhat arbitrary for us. The one thing that we could make a choice on is that transistors typically have different gains for different collector currents. So they vary between 40 to maybe 500 or something, and depending on how much collector current it is, you may be somewhere on that waveform. So let's say we want more gain, so we'll pick a larger collector current, maybe something like 50 milliamps. You could also choose 1 milliamp or 10 milliamps, but let's say approximately 50 milliamps gives us a good gain. So we have these two constraints. We have VCC and IC. So with those, we can start to actually calculate some of these values. So we want this point here to be around halfway of VCC. That way we can have the most room to swing our output voltage. So in that case, if it's half of VCC, then it's going to be 6 volts. Now we can calculate RC, because RC will be a 6 volt drop. and divided by 50 milliamps will give us the value. This is, let me look it up. This is 120 ohms. So we've selected our first component value, 120. Okay, so next up is the emitter resistor. So how do you pick this value? So this is one of those rule of thumbs I was referring to earlier. So you don't need a strict value here, but the way you pick it is you say, I'm going to take around 10% of VCC to drop across this resistor. So in that case, it would be 1.2 volts. We know that emitter current is approximately equal to collector current. So we say 1.2 divided by 50 milliamps. And this one is 24 ohms. So 10% is a good rule of thumb people have found for getting the stability you need without taking away too much voltage for your swings. You can go larger values if you want more stability, but keep in mind you will reduce the voltage headroom to swing. And that's because if this value is too high, you may clip when you get into saturation. So that is why you choose around 10%, but again, you can modify it. For this bypass capacitor, unless you're getting into strict like analog calculations, it doesn't matter too much. I'm going to pick 100 microfarads just so that it will have a very low resistance that will let it not have too much dissipation for the AC signals. That might actually be too low. Maybe it needs to be like 1,000. I'm actually not sure. You can calculate the impedance, which will give you the AC value for analysis. This is actually a very low emitter resistor, so you'll probably want something that's like large enough to be small. Okay, so that's this side. We've already calculated all the values. Let's go to this side. This one is a little more involved. So how do you pick these values? Let's say the top side is R1 and the bottom side is R2. So the first thing I'm going to do is determine what is the voltage at this node, VB. So since we defined earlier that VE here is going to be 1.2 volts, and we know that there is around a 0.6, 0.7 voltage drop across VBE, we can say that VB will be those two things added together, which is 1.9 volts. The next thing I'm going to do is determine how much base current do we need. So we calculated the collector current, which was 50 milliamps. So I'll put that here. Base current is collector current divided by the current gain. In this case, we can just approximate that it's 50. It could be 100, it could be 300, it could be 40, but we'll just pick a gain value of 50. With those choices, we get a base current of around 1 milliamp. So we know that there's going to be approximately 1 milliamp flowing through here. So this next calculation is going to be, it may seem weird, but what you want to do is ensure that the current flowing down this way through R1 and R2 is much greater than the current going through IB. Why is that? Well, when IB is fluctuating from this AC signal, you don't want your bias point to be affected too much. So when you have a large amount of current flowing through R1 and R2, these little fluctuations of 1 milliamp, which will come from either R1 or R2 depending on if the signal is positive or negative at that point, they won't impact the DC point that much. For example, let me do a little graph. Okay, so instead of a graph, let me demonstrate this in a different way. So if your bias point is being set by this resistor divider, for now we will ignore the BJT and the voltage source, or the audio input. So the value here is caused by current flowing through this joint and through this joint. So if I then now will add in the audio input, if I start inputting current through here, it's going to take the path either down or this way, because we know that there is current already flowing through this top point. So that means that the current flowing through here, and we'll ignore the BJT for now, will cause a voltage increase at this point, because the current will flow through here and then down. So this fluctuation will cause a voltage shift here. The question is, how much voltage shift will it cause? So if you imagine it like this, let's say that total there is about 100 milliamps running down without the audio input. And that creates a voltage of, we can say maybe just 1 volt. So if I now inject 1 milliamp into the system going down, that means that instead of 100, it's going to be 101, which means that the voltage is going to shift, if we assume perfectly linear, it's going to shift by 0.01 or something. So that's a very small fluctuation. So you can see how when we make the current running through the resistor divider large, small current fluctuations caused outside will not change this voltage as much. And if we did the reverse, let's say you only had 1 milliamp flowing through it, and it gave you a voltage of 1 volt here. Now, we say we dump 100 milliamps in from the input. You're approximately going to 100 times this voltage. You're going to get 100 volts instead of 1. So that is why you choose a much larger current running through it than opposed. And if we can add the full circuit for now. So if we just go ahead and do this. Now, keep in mind, we are limiting the base current because of this emitter resistor down here. If you have too much base current, then that means that the voltage here will increase, which, because this is just a diode drop away, this voltage will increase as well, which means that you will have less current flowing from this top point down, which means there won't be enough base current to supply it, meaning it'll stabilize. So because of what I just described, you will have a limited base current, and it's going to be relatively small. Actually, it's going to be exactly what we described earlier. It's going to be the gain IC divided by the current gain, which is, in our case, around 1 milliamp. So we know that some current will fluctuate through this system here with 1 milliamp. Actually, let me rephrase. It's not really going to fluctuate. It's going to take 1 milliamp for the DC sense. So now if we add as well the AC input here, this will cause some minor fluctuations over here, which will shift this VB by some small amount. And that slight change in VB here is going to cause the current running through here to slightly fluctuate as well. And current may not just go down here, maybe some of the current also flows through the BJT as well. That's getting more into like the exact details, but in practice, the current here will cause this voltage to fluctuate a little bit, either through sending current here, which modifies the voltage, or maybe by actually sending some current directly through it. Okay, so with that out of the way, how much more current do we need to flow through these resistors for this to work? And people generally say 10x. So we know that if there's going to be around 1 milliamp flowing through here, we'll say that we want 10 milliamps flowing through here. So we can calculate this now. We know that VCC minus VB divided by R1 will equal the 10x IB, which in our case is just going to be 10 milliamps. So shifting this around, the value actually will become 12 minus 1.9 divided by 10 milliamps, which will give us 1010 ohms. And we can do the same calculation for the bottom resistor. This one will just be 1.9 divided by 10 milliamps to give us 190 ohms. So we have picked all of our values, R1 will be 1010. This will be 190. And this capacitor is similar to this emitter degeneration capacitor, or I'm sorry, the bypass capacitor here. Just pick a large value for the most part, unless you're getting really into AC behavior. For practical amplification, just a large enough value usually would work. So yeah, we now have selected all of the values that we're going to use. And an important note is that when you actually put a circuit like this together, it probably won't work first try. And when I say it won't work, there will be some issue where the bias point is not 6 volts or something is wrong. And you can diagnose it usually to variations in the values. When you put in a 190 ohm resistor, if you do put a 190 ohm resistor, it's going to vary by some amount, 5%, 1%. Another point is that 190 ohm resistors aren't very common. Usually resistors fall under the E24 scaling, so the closest value would probably be 180, which means that your calculation is kind of thrown off because you have to use the resistor values that you have access to. So you may choose a 180 and that might throw off the calculation a little bit. The good news is that usually you can just switch out values until it's approximately good. So a good rule of thumb would be if the VB here is 12 volts, that means you don't have enough current flowing through IC. And that's probably because your bias point over here, something's wrong. Either it's these resistors are the resistor divider is off, or they're too large, or maybe your emitter resistor is too large. The point is you can kind of go through it and figure out, okay, if I don't have any voltage here, that means no current's flowing, which means there's something wrong with the generation of that current. And yeah, so that is a practical example. I'll do one more example where I actually do account for output current. Okay, so conceptually this next one is going to be just slightly different, but pretty much the same. We're going to have some audio source here. Oh, that's very different. Runs through a class AB amp. Except this time, instead of going to an ADC, we're actually going to feed this into a speaker. So I actually don't know the symbol for a speaker. I'll just symbolize it as just a regular resistor. But that is a speaker. That's going to make sound. So now it becomes a little more interesting because now we have to think a little bit more about what kind of currents we're selecting. So let's say you have 4 millivolts here on your signal still, and you want to make the speaker semi-loud. So that depends on how much current runs through it, which means now we have to think about what kind of voltage gain we need. So let's just say you want to dump an amp into this. So that means you're going to need 1 amp flowing through here, which to get 1 amp through an 8 ohm resistor, you need 8 volts. So you're gonna need 8 volts if you're going to give this thing an amp. So that means for our voltage swings, our headroom, we're gonna need a much larger VCC than last time. Let's just pick 32 to give us plenty of room. Okay, so we have VCC equals 32. The next thing, as we said earlier, we need to decide how much collector current do we need. So it is generally good to have more quiescent current than your load, than your load's going to require. Because if your load is going to fluctuate 1 amp from peak to peak, or 1 amp amplitude, whatever, you're going to need that variations to not cause your system to clip. So that means that you probably want maybe 2 amps or 1.5 amps running through it. That way, when it's at its midpoint with 2 amps, 1 amp will not cause it to fully get rid of its voltage, or cause any clipping, I should say. Okay, to reiterate, we are choosing VCC 32, so we have more voltage swing room because we want to swing 8 volts. We want to swing 8 volts because we want to run an amp through the speaker. And because we want to run an amp through the speaker, we're going to pick a larger collector current around 2 amps so that those fluctuations don't cause clipping. So we know actually the same thing as earlier. We know that this VCC midpoint is going to be about 16 volts. So then we can say 16 divided by 2 amps will give us RC, which will be 8 ohms. So we've selected 8 ohms. We know that we want around 10% of the VCC for RE. So that's going to be 10% is 3.2 divided by 2 amps, which will give us, I'm just going to say 1.5. We both, actually no, 1.6. I can do that math. Okay, so then after that, we just have to calculate R1 and R2. Assuming a gain of 50, we can take away 2 divided by 50 to get, I think that is 200 divided by 50. I think that's 40 milliamps. Yeah, so we need 40 milliamps into the base because we did the IB equation. Then we can calculate what R1 and R2 need to be. So we can say this is going to be 0.7 plus 3.2 to give us what VB is. So 3.2, that's about 3.9 volts. So you know that for R2, the calculation is going to be 40 milliamps divided by 3.9 volts. R1 will be 32 minus 3.9 divided by 40 milliamps. 702 over here. And on the other side, it's going to be 97.5. And so there we go. We calculated all the values. You may be a little unhappy about this portion, and we can get more into detail. This is starting to get into the territory where I'm not as comfortable explaining, but the idea here, if you want to get more precise than approximately doing double it, is the idea is you have you can model the impedances to see how current gets split. So let me go ahead and erase some stuff. My cat has showed up. He's expecting dinner soon. There he is. Okay. I'll feed him in a second. So let's model the impedances. Well, over here, this can be modeled as, we'll say, R load, and this can be modeled as RC. When you do AC analysis of a BJT, it looks something like this. R load, RC. The main point is that you will have RC, RL, and I think here RE would be down here, but we'll ignore it for now. The main point is that you have a certain amount of... What you doing, dog? Sorry. You're basically going to be splitting the current, I total, between RC and RL. Which is your load and your collector resistor. So if the change of I is 1 amp, which is what we're saying we want to do kind of peak to peak here, then between these two it's going to split 1 amp. And it does it as a current divider, which is I total times, we can say, if we want to know how much current's going through the load, we do RC divided by RL plus RC to give us I load. I will double check this calculations, but I'm pretty sure this is how it works for the most part. So it's simply just going to be, that's how you get a more precise calculation. So in reality, you may ask, how much current do you need to flow through I total to be in order to get the proper load? That might not be precisely 2 amps, it could be something else. So if you know that you want 1 amp through IL. Then you know that RC, let's say we can do our calculations, 8. Let's say we have a speaker which is also 8 ohms, so then it's just going to be 8 plus 8 times I total. So I total will split the current in half. So you need a total of 1 amp of not 1 amp, I'm sorry, you need 2 amps of, I'm not sure if this is in frame. You'll need 2 amps of I total, which I actually did not mean this to be the case, but it looks like it works out perfectly. So you need your fluctuating current to be 2 amps in order to get 1 amp through it, because the loads are so similar in this scenario. Yeah, so that explains it. I think my camera battery is getting low, so I'm going to cut this one short and I guess finish up in the next one. So I went ahead and made the circuit for the first iteration, and there were a couple modifications I had to make, which I actually wrote down in this schematic here. Instead of a 120, I used a 100. Instead of a 24, I used a 22. Instead of a 190, I used a 150, and I used a 1K instead of the 1050. That was just because those are the resistor values I had on hand. So because of that, we will see some minor modifications, but if I turn it on, we can see on the oscilloscope that their voltage, and this is tied to the collector currently, we see that we have around 7.74 volts. And the truth is, we had a reduced collector resistor, so it's going to have a less voltage drop for the collector current. But we do see that it's around 53 milliamps, so it is pretty close to the actual collector current we wanted. So besides that, I'm going to turn this off because it will get pretty hot. Those resistor values are not built for it. But as you can see, we selected some values here and it worked out. So this is the modified circuit. I have a input signal coming in via a capacitor, and I actually have the load over here, but it's currently disconnected. When I want to reconnect it, I will use this capacitor here. So when I turn on the power, right now it's measuring what's at the collector terminal. And we're seeing around 2 volts peak to peak, which is pretty accurate with our signal gen, which is doing 1 volt swings. And so it's currently just taking the full signal. And now if I were to connect the capacitor, in fact, I will leave this on the oscilloscope. Once I connect it, we do see, that's if I connect it in. Once I connect it, we see a voltage drop here. And that's now because it's splitting this voltage with the other load. So now, instead of having the oscilloscope probe the collector terminal, I'm going to have it probe the load. And we're seeing around 1.6 here. Alternatively, I gotta bring this back up. Let it do its measurements. Honestly, around the same. And that somewhat makes sense because the load is identical to the collector resistor. They're both 100 ohms. I will turn this off because the resistor is getting quite hot. But without doing further calculations, that seems around right. The capacitor here is quite large, so at this frequency of 1 kilohertz, it should act basically as a short, meaning it splits the current equally among the collector resistor and the load resistor. So that seems to make sense. That concludes this video. If you have any more questions about Class A amps, feel free to leave a comment and I'll do my best to answer them. I hope I didn't have any mistakes in this video. If I did, point them out so that other people don't get misled, but I'm pretty sure it was... It's been about 2 months since my last upload. I did not want it to go that way. I'm still trying to figure out how to balance my work life and my personal, and since both of them are engineering right now, it's tough to motivate myself when I get home. But I do like doing this, and I want to continue doing this, so expect some more uploads soon. That video I've been working on for 2 months, kind of been half doing it, will be out somewhat soon. I just finished a big portion of it, so I feel like that'll be out soon. Although I will be out of country for 2 weeks starting next week, so maybe it won't be out. We'll see. But yeah, thank you for watching.